This video is looking at another thing that's important in the sciences, and that's significant figures. There's three things that we are concerned with significant figures. The first is when we are taking a measurement, writing down that number to indicate the correct amount of precision given whatever tool we were using to take the measurement. The second is reading someone else's measurements and understanding the precision that they were using. And the third is doing calculations with those measurements and correctly reporting to the right precision what the answer should be. So first, looking at when we are recording our own numbers that we have collected from some device. So whatever sort of scale we're using, whether it's a balance to measure mass, a ruler to measure distance, or so on, our number is only as good as the tool we're using. And some tools have way more precise gradations on them than others. So when measuring, we need to state all the certain figures, which we can read off of the device, and we usually estimate one extra digit, because on most devices we can say, oh, this is between 3 and 4, or this is between 7 and 8, and we make an estimate as to exactly what it's at. So that last digit is called the uncertain digit, but it's still significant because it's part of our measurement. So our examples that we have here, we have some pictures with a measurement shown by the arrow. So if we look at this first one, we can see it's clearly between 10 and 20, and we've got measurements that we can count over, and we can see it's between 4 and 5. And we have to estimate where exactly is that arrow. Is it a little closer to the 5? Is it a little closer to the 4? And so we make a judgment call, and we estimate it to that one digit. So this one's not right in the middle. I'd say it's a little closer to the 5. So I would estimate it at 14.7 grams. Now note that this last digit was an estimate. So you might look at it and say, no, I think it's a little closer to 5 than that. I'm going to estimate it at 14.8. And that's okay, because that last digit can vary slightly because it is our uncertain digit. So the way you read it versus the way someone else reads it might be a little bit different. So with the next one, again, I see my gradations. This is 100, this is 150, so that tells us we're going up by tens. 110, 120, 130. So between 120 and 130, I have to estimate just how close it is to that 130. I think this one's a little closer than the last one. So I'm going to call it 128. Whoops, fingers on the wrong keys. And again, don't forget units. Last one here. I can see my divisions are going up by 0.1 if this is 8 and this is 9, so that's 8.1, 8.2, 8.3, and we're partway to 8.4. So I would estimate that that's pretty close to halfway, so 8.35. Apparently my typing could use some help. There we go, 8.35. Next one, my scale is a little harder to read because my divisions are a little all over the place, but I can see that this is between 140 and it's getting close to 145, but it's past 144. So again, this one I probably have a higher degree of uncertainty because my divisions are so close together at that point, but we could estimate it to the nearest half, so 144.5 pounds. Sometimes on these sorts of estimations, you'll see a margin of error shown where they put plus or minus, you know, how much it might vary by. So plus or minus 0.1. This one, as I said, because they are a little closer, I would probably be going plus or minus. I might even go so far as 0.5 depending on how much I trusted this particular scale. Okay, another one, we're between 0.2 and 0.3. And so if we look at that, 0.21, 0.22, 0.23, 0.24, and we're somewhere between 0.24 and 0.25. It's a slightly closer to 0.24. So I'm going to go 244. Now the next few are liquids, and liquids are unique in that they curve due to surface tension. And that curve makes them a little more challenging to read, but the tools that we use in the lab are all designed to be read with that in mind. So we read them looking at the bottom of the curve. Now that curve is called the meniscus. So you may hear that you read them to the bottom of the meniscus. So my first one, I'm going up by 100, 150, 200, 250, 300. I'm looking across from the bottom of this and trying to guess where that falls. So I really can't estimate all that closely. I might guess 250, I might guess 240, but it's definitely, that's as much as I can be certain of. So I'm sure it's between 200 and 300. But because my gradations are so far apart, that's about as sure as I can be. So I'm going to go with 250. So my next one, see, my font is a little small there. Let's move that up. So my next one, we're looking at a graduated cylinder, and it's between 20 and 30. Again, my gradations are going up by 5, so this one would be 25. It's a little between 25 and 26. So I'm going to estimate that one to be at 25.6. Again, don't forget the units. A pipette is a really precise thing to measure, so these three actually gradually got more precise. So a beaker is not very precise, a graduated cylinder is more precise, and a pipette tends to be the most precise of these. Although in this particular case, the pipette's looking kind of similar to our graduated cylinder. We're going up by 1s. Also notice that this one is backwards, right? It's looking at how much is being let out. So some devices, like pipettes or burettes, are sometimes, burettes are always marked this way. Pipettes sometimes are marked this way, where the markings go backwards on how much is let out. So when I'm reading this, I'm actually going 15, 16, 17, 18, 19, and I see it's close to that 19, but it looks to me like the curve is a little below the 19, which means it's going towards 20. I'm going to go with 19.2. Again, one estimated digit. Graduated cylinder, again going the other way, so we're between 4 and 5, so our gradations are 0.1. I can see, if I look there, it's looking really close to on the line. That is the third line above the 4. So I might estimate that one as 4.30. I might estimate it's right on the line. But again, I can't be totally certain about that. So when I look at that value, I'm having that plus or minus, whether I write it down or not, right? I'm realizing that this is saying there's about 100th milliliter wiggle room on that one. So it might be a little above or a little below. It's a little hard to read. Okay, thermometer in Celsius. So when we look at this one, again, my divisions are far enough apart that when I'm doing that margin of error, I'm probably going to say plus or minus a half in this case. So I know it's clearly above 35. It looks like it's about halfway to 36. So I'm going to say 35.5 degrees Celsius. But again, I know there's some wiggle room there. Whoops, and I pushed over my measurement there. One thing I will point out is that, one extra thing I will point out is that on digital balances or other digital devices, we take the reading exactly as it is off the digital device. So if our balance, for instance, says 13.47 grams, we're going to write down 13.47 grams, exactly like it is, because that balance is precise to however many digits it displays. So, as I was mentioning with burettes, they are designed to be read backwards, right? It's how much we're taking out. So when I read this, this is 19. This is also showing you when you are actually doing that measurement that the way you're looking at it can make a big difference. So you want to make sure your eye is perfectly level in the lab with the bottom of the meniscus, because if you're a little too high or a little too low, you end up taking a different reading. So that's counting, writing down our values correctly to the correct number of significant figures. So the second thing is looking at someone else's values and saying, okay, well, how many significant figures does that have? So we have really only two rules, and that's non-zero digits are significant and placeholder zeros are not significant, but the other zeros are. Now, most people like to break the placeholder zeros are significant rule up into sort of some sub-rules. And the sub-rules are these A, B, and C. So leading zeros are never significant. They are just placeholders. If you look at, well, let's go through all the examples. We'll start with this one. So my first one, if I have 248 kelvins, right, all of those are not zero. That says they're all part of the measurement. So we have 3 significant digits. By the way, the term significant digits and significant figures gets used interchangeably. So if you're hearing some places they're saying significant digits or sig digs, and other places you're hearing significant figures or sig figs, they mean the exact same thing. So next example, my leading zeros are never significant. So 0.003, those first zeros are really just pushing the 3 over and saying get in the right spot, right? So the 3 didn't belong in the tenths place, didn't belong in the hundredths place, but it does belong in the thousandths place. So the 3 is the only thing that's really been measured. The zeros are just there so that the 3 is in the right place. So we only have 1 sig fig on this question. If we look at 0.024, again, those leading zeros, not significant. So we have 2 significant figures there. Trailing zeros have an if in their rule. So that's kind of important. So they're only significant if there's already a decimal point. So if I have 172.00, those zeros aren't pushing anybody over. They're just there to say this was measured precisely all the way to the nearest hundredth of a kilometer. So that actually has 5 significant figures. Whereas the number 170, that 0 is only there to push the 7 into the tens place. Without the 0, right, that measurement would be 17, a very different number. So the 0 is there as a placeholder. Now, one thing that sometimes confuses people is the terminology significant means something a little bit different when we're speaking of it in a scientific way than when we're talking about it in everyday language. Because if you look at this number, 170, if I took out the 0, it would be a different number. So that 0 is important. And in everyday language, important and significant are kind of synonymous. But when we're talking about measurement, significant means it's part of the measurement, right? So not that it's not important, that it's part of the measurement. So when we have that 0 there, it's not part of the measurement, it's only 2 significant figures. Our very last example in this group is kind of a special one to pay attention to. If we have a number like 170 and we actually write down the decimal, we don't actually have to put that decimal there. But sometimes in science, if we're putting down a series of numbers and they're all to the nearest 1, and some of them just so happen to end up right on the line, to show that it's significant, we'll put that decimal there. So we've got that expressed decimal. My 0 is significant. That one's got 3 sig figs. Oops. Okay, that one wrapped around. Let's format this so it's a little easier to read. There we go. The last one, and this one doesn't tend to give people as much problem. Zeros between significant figures are significant. So if I have 10.54, they're all significant. So that's 4 sig figs. 10.001, also all significant. So that is 5 sig figs. So the hint that I have on there, some people like to actually physically draw through their numbers when they're figuring out their significant figures. So if the number has a decimal, we start at the left and cross out the zeros until we run into a number that's significant. So that would be like this one here. So we basically go do 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 do. Those ones aren't significant, but the 3 is, so I got to stop. Right? I've got a decimal, I start from the left. Same thing here. I've got a decimal, I start from the left. It's like, oh, well, I've already run into a significant digit, so the rest are going to be also significant. Same thing here. But if we don't have a decimal, we start from the other side. So here I would start over here, no decimal, but I've already run into significant figures. Here we have no decimal, so, oh, there we go, 2 significant figures. Here we have a decimal, so we start from the right. And same thing here. I didn't give very many where we did not have a decimal. Might need to put a few more examples like that. Now, with numbers like 170 kilometers, where the zeros are at the end, sometimes it's unclear whether it was measured to the nearest kilometer or whether it was only measured to the nearest 10 kilometers. So to avoid what's called the ambiguous situation, we sometimes use scientific notation. So something like 200 degrees Celsius, if it's measured to the nearest degree, we could show it as 2.00 times 10 to the 2 degrees Celsius. So we can see that's to the nearest degree. Another thing you sometimes see, and remember this is only before the decimal, because behind the decimal is not ambiguous, we can put this line over top. So this is different than when we put a line over top of a repeating decimal, because this is not behind the decimal. This is in front of the decimal. So what the line does there is it says, hey everybody, look, this number's the last significant digit. This is the one that's estimated. This is the one that was measured with some tool. So the line helps us figure that one out. And there is a third rule. I guess I shouldn't have said there's only 2 rules. The third rule is not referring to measured values, though. It's referring to exact values. So those do not come from measurements. They either come from definitions or from being counted. So counted are things like 10 people. Definitions are things like conversion values or constants like pi. Right? They can have as many significant figures as we need them to have. So I do have a few examples here, and I'm just going to quickly go through and say the answers. I'm not going to type all of these ones in, but I'm going to use that drawing a line through thing that I was talking about earlier. So if it has a decimal, we start from in front. If it has no decimal, we start from the back. So here, everything in front is not significant. Every 0 in front, so there are no zeros there, so we've got 5 significant digits. Next one, we have no decimal, so we start over here. 3 significant digits. Decimal, start on the left. 1. Decimal again, but we've got a 0 at the end, so that one's got 2 significant digits. Now 12 boxes is tricky, because it looks like 2 significant digits, but it's not actually. because 12 boxes is not something we measure, it's something we count. So it's got infinite significant figures. So how we show infinite, we could either write the word infinite, or we can put this symbol that looks like a sideways 8. That word wants to make disappear on me. 12 meters has a decimal. We're going to start from this side. It's got 2. $480 also has no decimal, so it don't count. I just realized I said this one doesn't have a decimal, and I crossed off the wrong side. That is 100% wrong. Let's fix that one. Oop. See, everybody makes mistakes. Good to realize. Good to check them and fix them. Someone has a decimal, so I started on the wrong side when I was colored with my pen. Really, we would be not counting the things in front, so it has 3. This one has no decimal, so it's also got 3. So that was our second thing with significant figures, counting someone else's. Third thing is looking at what we do in calculations. So with calculations, there's a couple things to check out as being important. I see I've got some outdated things here. We're using a different text. So the rules for rounding, most people are familiar with the first two. Sometimes you'll see textbooks and publications use the third one here. So if the number following the digit to be rounded is less than 5, we drop the remaining digits, replace them with zeros if they need to be replaced. If the numbers following the digit to be rounded is greater than 5, we add 1 to the digit, then drop the remaining digits. So this is sometimes referred to as rounding down and rounding up. And sometimes you will see when it's exactly 5, there's another rule. So some texts use, say, 5 and more, and some have this special rule for exactly 5. So for exactly 5, if it's even, we keep the digit as is, and if it's odd, we go up, and it's known as the even-odd rule. We only round at the very, very end of our calculations, never ever round things twice, so you don't round in the middle of a calculation and then round your final answer when you get to the end. Nope, just round it once. So rounding the following values to 3 significant figures, I am going to pause here. I would suggest you actually pause for longer than I do by pausing the video. And as you pause, try these 6 questions and then start it up again to get the answers. So only one of these questions has the potential of having that odd even rule, and that is question B. So in terms of Chem 181, for those watching that are in my Chem 181 class, the odd even rule is acceptable, but it won't be enforced. So if you choose to reuse it, it's fine, and if you choose to not use it for the purposes of this course, it's also fine. Where it becomes really important to use is when you are doing calculations with very long lists of numbers, like when you've collected a huge amount of stats on something. It's less important with the sorts of calculations we'll be focusing on. So there's your answers. Hopefully you got them all right. And now the next thing that we can do operations besides rounding is multiplication and division, addition and subtraction. And I'm starting with multiplication and division because most people find the rule for multiplication and division a little easier to remember. And that is simply count up how many significant figures you have in each number. The one with the fewest is what's going to determine how many you should have in your final answer. So if you have one that has 7 significant figures and one that has 2 significant figures, your final answer can only be 2 significant figures. So if we look at these when we would perform these calculations, we could get a lot of decimals for this one, right? If you use the pi button on your calculator, it'll calculate it to as many decimal places as your calculator can display. But when we round it, we want to round it to only 3 significant figures, because the 2 only has 3. The 2.00, those zeros are significant because they're after a decimal. We want that to be to 2 significant figures. So when we round that, we get 6.28. Don't forget units on these things. So in this case, it's meters times pi. So pi has no units, so it's just 6.28 meters. Second one, we have 2.00 with one of those lines on top. So remember, that tells us there's our last significant figure. So we've got 3 sig figs divided by 3 seconds. That one's got 2 sig figs. So you punch that in your calculator, you're going to get 66.6 repeating, right? It's just going to show a whole bunch of 6s. Depending on your calculator, the last digit might be a 6, it might be a 7. But bunch of 6s. So only 2 significant figures. We're going to go say 66 and our next digit's a 6, so we got to round that up to 67. And our units, well, we don't have units that we can cancel or do anything with, so we just have meters divided by seconds. The way we usually show that with units is we say per, so meters per second. So this would be a velocity unit or a speed unit. Next one here, again, pause, type it into your calculator, see if you can find what your calculator spews out for an answer. It should be spewing out 20,000, but it's 2026.5. Obviously, that is too many digits, because we have 2 digits here, 3 digits here, and 3 digits here. So we only want to round that to the least number of significant figures, so that's 2. Well, if we round this one, that becomes 2,000. And 2,000 doesn't look like it has 2 significant figures. So we need to decide, are we going to put that line on top, or are we going to write it in scientific notation? So I'm going to write this one in scientific notation. So 2,000 becomes 2.0 times 10 to the 3. The beauty of scientific notation is that every digit we use in scientific notation is significant. So we can always just look at scientific notation and go, boom, it's got that many significant digits, in this case 2. So that's half of this question, but the other half is figuring out these units. So if we look at this, we have moles times coulombs per mole divided by coulombs per second. And some people have issues with that. So let's take a look at what's going on there. So it's like fractions. Moles times coulomb per mole divided by coulombs per second. And if you didn't know what the C stood for, it doesn't matter. You can still look at how do they cancel. So clearly, when I have a fraction multiplied by something else, I can make this one into a fraction by dividing by 1. And my moles on top cancels my moles on the bottom. So now I'm left with coulombs divided by coulombs per second. And we know when we're dividing by fractions, we invert and multiply, so that becomes coulombs times seconds over coulombs. And so we can see, just like our moles canceled, so do our coulombs. So cancel the coulomb here with the coulomb here. For some reason my multiplication keeps disappearing. And we're left with seconds. Not happy with this pen tool telling me I can't put an X there. Okay, it seems to be staying this time. Okay, so that's multiplying and dividing. Adding and subtracting is much more complex, shall we say, because for adding and subtracting, we have to make sure that our decimals lined up. And with some numbers, that's pretty easy to look at. Others, it's a little more difficult. So when we are doing adding and subtracting, we go by our rule, which, did I say it up here? No, I didn't. I said it here. Looking from left to right, the first digit that's insignificant, non-significant in any number in the column, that makes that whole column non-significant. So if we look from left to right, here we have significant all the way up to 2 decimal places. This one is significant only all the way further, all the way up to 3 decimal places. So wherever I sort of run out first with my decimal places, that's the one I'm going to say, okay, we're going to stop there and round there. So our initial calculation on that one, we're going to get 177.711. I see I'm missing a 1 here. Sorry, it's 771. That's what I'm missing. And so when we round it to that least number of decimal places, it's going to be 2 decimal places. This one here, again, it might be nice to just line them up. So when we put that in, we're going to have 3 zeros, a 3, a 2, and a 1 to make sure they're lined up here. Also notice when we're adding, we can only add and subtract things that have the same units, and our final answer is going to be units, right? It makes sense. If I add centimeters plus more centimeters, I'm still going to get centimeters. So when we do this calculation, we're going to get, give me a second. $9,753,543. Let me get that lined up a little better. There we go. So when we round that one, we can see, and again, my pen tool decided to make things disappear. One of my zeros disappeared. So we can see on this one, we ran out of placeholders on the thousands place where that 3 is. The other one, we could go all the way to the nearest 1, but it's which one did we run out of first the way we read it. So as we read from left to right, I can see I'm running out at that 3 because those zeros aren't significant. So when I go down from there, right, I'm going to be at this value right here. And so that's the one I have to look and see what's past it. Well, it's a 5, so I'm going to round up. It's more than 5 actually, because it's 543. So I round up to my next value, which in this case is 4. When we're doing this in scientific notation, sometimes we're lucky and our scientific notation is the same power, but sometimes we're unlucky and we've got 2 different powers. And we can't line up the decimal if we have 2 different powers, because that power of 10, remember, really tells us where our decimal place belongs. So when we do these questions, we have to move our decimal over to make them match. There is not a one right way to move them. I actually strongly suggest you put these in your calculator and then move them so that you can match it up with your calculator. So your calculator will do the adding and subtracting like that, but your calculator won't tell you how many significant figures you should have. So you can use the calculator to figure out, okay, what do I get when I add and subtract, but then use your matching things up to let you know what you have for significant figures. And I see when I type these in, I obviously didn't follow my own advice because we're going to end up with an extra step. In some ways that's good though, because when we get that extra step, sometimes you do get that extra step and you need to know how to deal with it. So let's take a look at this one. So if I just choose to move these both to 10 to the 5, and again, it's arbitrary. I could choose to move them both to 10 to the 6. So the 10 to the 5 one stays just like it is. The 10 to the 6 one, well, that's getting one smaller. So if this side is going down, the other side of my number has to go up, right? So my power of 10 goes down. In order to balance that, this one's got to get bigger. So that's why it became 45. And then we can do the subtraction as we usually do. Now the problem is, as I said, sometimes you get an extra step because that extra step, it's not in scientific notation, right? We've got two numbers in front there. So we need to move that back over, which means that's getting smaller. My power of 10 gets larger. So be careful with that. Negatives are sometimes even trickier because you got to remember when you're going up on a negative, it's the opposite direction that when it's in a positive, like -2 is bigger than -3. It's important to note that. So this time I went to both to the -3. So the first one stayed the same. If I'm taking this down to -3, because that's smaller than -2, I've got to take my other one up, so it becomes 28. So this side's going down, this side's going up. Again, when I add those two, I ended up with something not in the scientific notation. So we have two steps to do in this one. This one over here, we didn't end up having to round because when I had the same power of 10, I had the same number of decimals, right? So we round using while we're at that power of 10 step. Here, I do end up having to round because I've got 3 decimals in this number, only 2 decimals in this number with this power of 10. So really my last significant digit is the 2 decimals when I'm in 10 to the -3. So it's going to be that 7. Even when I change it to scientific notation, that 7 is still going to be my last significant digit. Just because I've moved my power of 10 doesn't change which digit is my last significant digit. So my last step, I was actually doing both, rounding it to that last digit and changing my power of 10. So again, from 3 to -2, that's going up. So this part has to go down, or more to the point, this is getting smaller. This one's got to go up. Now my last one here, when we are subtracting something like this, well, these ones have pretty small, this one doesn't have any power of 10. This one's got a pretty small power of 10. And even the previous one, when you're dealing with some small powers of 10 like that, you might say, well, if I want to line up the decimal, I'm just going to convert them to standard notation. And that's perfectly okay. Right? If it's like 10 to the -15, kind of hard to do. But when it's 10 to the -2, not so hard. So use standard notation if you find that easier for those smaller digits. So then it's easy to see I've got 2 decimals here, 3 decimals here. So when I round, I'm going to round to 2 decimals. So multiplying and dividing, it's the least number of significant digits. And adding and subtracting, it's the least precision, which we sometimes refer to as decimals, but that's not quite accurate. Because if we have a very large number, like in B, there's no decimals, but it's your last significant digit when we're looking at precision. One last thing to note, if we have multiple operations, as I mentioned earlier, we only round once. We never round twice. So if you have something like this where you've got multiple steps, you still do all the steps, and you still follow your usual order of operations. So first off, there we go. We've got to do what's in the brackets. And inside the brackets, we have some multiplication, so we do that first. And we have 3 sig figs times 3 sig figs in that multiplication, so nothing changes significant figures-wise. Then we have to do the subtraction, and we actually end up losing a significant digit in that subtraction. Because when I subtract that, I get 0.554, but I'm subtracting my rule is number of decimal places. And I've only got 2 decimal places in my 6.02. So when I round this number, I really only have precision up to that 5, that second 5. So because that's where my precision ends, I'm going to keep in mind that I really only have 2 sig figs there. But I'm not actually going to round it, right? Because I've not done my calculation. So I know in my head that's 2 significant digits, right? Or to the hundreds place. But I'm going to keep it all in my calculator or write it all down because I don't want to do any rounding until the very end. So my last step, I do that multiplication, and then I say, okay, I had 2 sig figs multiplied by 3 sig figs, so my final answer, least number of sig figs, is going to be 2 sig figs. So the rounding that we do on that one is a little bit confusing to some people because we started out, everything had more than 2 sig figs, and our final answer ends up only having 2 sig figs. But it's because we had to keep track, and when we did that subtraction, we ended up losing a significant digit. And that often happens with subtraction, that we either lose or gain. Well, with subtraction, it tends to be, if we're going to do something, it's lose. And with addition, we sometimes gain a significant digit because we're looking at precision, not significant digits, when we add and subtract. So that's the last of it. And we'll stop there.